Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll be continuing with our Routh Hurwitz Criterion, right? And this is a lecture 4, basically the continued version of the previous lecture where we had to stop. We were solving questions, so I have added many more new questions also here, and one interesting concept also to study. Okay, so and in this lecture we'll try to end our Routh Hurwitz chapter, right? So yeah, let's start with the question. So we have a transfer function, planned transfer function like this one, with a positive real parameter, like p is a positive real parameter, p is positive, the maximum value of p until which gp remains stable. So this time nothing is told, okay, they have told nothing, okay, about the OLTF and all those things. So this is I will consider this one as my transfer function itself. I will not consider this one as my what do you say, I mean OLTF, because they have told us gp to remain stable. So I hope you did this, right? gp to remain stable. You are not simply doing the CLTF. So you just see g and you just do g upon 1 plus gs, right? Don't do that, okay? Read the question, right? So they have told us that gp should remain stable. So if gp should remain stable, I will write my transfer function gp is equal to p square plus 3ps minus 2 divided by s square 3 plus 2 into s plus 2 minus b, right? So this is my basically gp, and this is not OLTF, right? Not OLTF. I don't even care. Okay, what is this? I don't know. Okay, because they have told us about this to find gp to remain stable. Okay, so I won't write this as OLTF. Okay, I just need to find the stability of gp. Okay, stability of gp. So what will my gp basically, like what is the characteristics equation? So characteristics equation is basically s square plus 3 plus p into s into 2 minus p, right? 2 minus p. Okay, this is basically my characteristics equation. Now this is second order system only, so we can simply equate the understand that the coefficients should be all of same sign. So this is 1 plus 1, so this has to be also greater than 0, and this has to be also greater than 0. So basically again I will copy that statement. Okay, where did the statement go? Here, right? Yeah. So again I will take one page. So again I will write my 3 plus p should be greater than 0, and my like this should be one of the conditions. So p should be greater than minus 3, right? This is one of the condition, and my 2 minus, okay, I will write this in different pen. 2 minus p should also be greater than 0, so p is less than 2. So these are my two conditions. So what are my limits on p? Positive parameter, p should be less than 2 and greater than minus 3. Okay, these are my limits on my p, right? So what do I see? Like we have to find the maximum value of p until which gp remains stable, right? So p is going above minus 3, and at 2 it will not remain stable, right? I can write 1.99999, it will remain stable. I have to write 2, then this is the maximum value. But at p equals to, what is happening? This is going to 0. Okay, so there is one pole at the origin. We won't talk about that, okay, because like we have to put some numerical value, right? We'll put p equals to 2, right? If we put p equals to just at the edge of p equals to 2, okay, just before that, just 1.99999, it is still stable. So yeah, my answer will be maximum of p equals to 2, okay, for stability. So here I will write as 2. Okay, so yeah, this is this question. Now let's go for another question. So we have the oscillation frequency of the system. The oscillation frequency of the system with characteristic equation are as follows. Okay, so like we have to find the oscillation frequency of this one. So what we can do, like we have been given the different frequencies, right? We have to find the oscillation frequency. So this system is marginally stable. So what we will do, I will just I will not find the row of zeros, right? So what we can do, so we can compute Routh table, okay, to find the oscillation frequency of this one. How you compute the Routh table? You know that you have like basically marginally stable roots. You will find the ROZ, and from ROZ you will find your roots, right? You will compute Routh table, okay, then find ROZ, then find the roots of the auxiliary equation of auxiliary equation, right? Then you find the roots of the auxiliary equation, okay. But this is the not the correct way, lengthy method, right? Lengthy method. So what do you do? Basically, my drawing is not that good. So okay, I need to delete this one. Okay, so yeah, you keep it over here and you make this smaller. Okay, so we make this smaller. Now what will be the method 2? Simply we did some similar question like this one, right? If oscillation frequency is given, you just simply put that in the equation. So for option A, it is given 1 radian, right? 1 radian per second. Okay, so let me like make these options very standard also. So yeah, this will be here and this will be here, this will be here, and this will be radian per second, radian per second. Radian per second, right? So this is radian per second basically. So this is 1 radian per second, 2 radian per second, 3 radian per second, and 4 radian per second. So if my oscillation frequency is 1 radian per second, then what does that mean? Where are my roots? My roots are at plus minus j, right? Plus minus j. So SP should be plus minus j. So I'll put this plus minus j over in this equation. Okay, put the oscillation frequency in characteristics equation, right? So if I put it here, so this becomes plus j whole to the power 6, 2j whole to the power 5, plus 3j whole to the power 4, plus 4j whole cube, plus 3j whole square, plus 2j plus 1. Okay, I will check what this is equals to. If this is equals to 0, then yeah, this will be my oscillation frequency. So what is j to the power 6? So j to the power 4 is 1, so that is gone. I am left with j to the power 2. And what is j to the power 2? It is minus 1. Okay, you compute, you will understand. So what I am doing, simply I am writing first j to the power 4, okay, then multiplying by j square. So this becomes 1 and this is minus 1. Okay, so this together is j to the power 6. So this is minus 1 plus j to the power 5. What is j to the power 5? It is basically j to the power 4 times j. So j to the power 4 is 1, so this will be 2j. Now what is j to the power 4? It is 1 itself. J cube is minus j, okay, and this is plus 3 minus 1, and this is plus 2j, okay, and plus 1. So what is this? Basically this is getting cancelled, plus 1 minus 1, this j, and okay, this j, okay, this j is still here, so this is plus 4j, right? Plus 4j, and this 3 is getting cancelled, right? 3 and minus 3 is getting cancelled, and I have minus 4j over here, right? Minus 4j. So yeah, I see that my equation is satisfying. So if you put the other values, right? If you put the other values, you will see that they are not satisfying. Okay, hence my option A is correct. Option A is correct. Okay, so here my option A will be the answer. Okay, so yeah, I have understood this question. Just whenever oscillation frequency is given, you can use this trick. So I put 2 questions to keep this in your head and memory, that we can also use this method also, else other methods will be very lengthy. So yeah, just be careful about that. So now this is the last question, and this is a very interesting question. So what is this question telling us? So we have to find the value of k such that the roots of the characteristics equation lie on the left of the line s equals to 1. So what is the line s equals to 1? Line s equals to 1 is this one, right? So let me first visualize, show you, then you will understand this question. So line s equals to 1 means this is my sigma plus j omega axis, right? Sigma plus j omega axis. Okay, so this is my sigma plus j omega axis. What is this? So if this is my sigma plus j omega axis, this means what does my line s equals to 1 lie? So what is this line? This line is s equals to 0, basically s equals to 0 plus j0. Now s equals to 1 means it is real, so it is lying over here, and throughout this, right, my real part will be only 1. My real part will also be 1, but my omega can vary. That is basically line, right? So I can write s equals to plus j omega. So my imaginary component is varying, okay, but my real component is fixed. Okay, just we did the root analysis in the what do you say, time domain parameters, right, where we made horizontal movement, vertical movement, all like that thing. So this is like a vertical movement itself. My roots are moving in the vertical direction. So basically this is my s equals to 1 line, right? S equals to 1 line. So now what are they asking? They are not asking about how many roots are on the left hand side of my j omega axis. They are asking me how many roots are on the left hand side of this s equals to 1 plane. S equals to 1 plane. So it is very important, right? How many roots are left hand side of this one, not on here. So also I have to take care of this one. So I just simply can't blindly apply Routh, because while we apply Routh, what we should do? We should find that how many roots are on the are on the right hand side, basically how many roots are positive, right? How many roots are positive with the help of Routh. That's what I used to do. Okay, but now I won't be able to do this, because this part is also positive. Okay, if some root lie between 0 to 1, that also includes my answer, but I don't want to include it. Sorry, roots lie in the left. Okay, so yeah, I don't want to include this part, right? Because I want to just include I want to also include this part this time. Okay, because yeah, because basically if I would have calculated here, my answer would be all of this, right? Whatever roots are on the right hand side, my answer would be this. But this time I am calculating from here, so sorry, I don't want to include this one. So I want to include only this part. How many roots are on the right hand side of this s equals to 1? Then I will subtract that one with the total number of roots, and I will get the total number of roots here. Okay, so as we solve, we'll understand. But now you solve this one and pause this one, try to solve this one. Okay, what things you might do is like, can we shift this one, because I only know how to find roots around the origin. Can we shift the axis and all those things? Let's you try to understand, and then we'll start the solution. Okay, so what do? You just simply say that I know my like internal product and external product condition, and you will multiply 118 times 10, and you'll see your answer, right? But no, this won't be your answer. Why? Because this time, right, I have to find around s equals to 1 line, not s equals to 0 line. So this is my s equals to 0 line, right? So basically, right, I don't want to find my roots around this line, right? I don't want to find my roots around this line. Okay, so yeah, I want to find my roots around this line. So what should I do? So can I do something and change my variable so that my variable is around s equals to 0 line, but actually I am finding the location at s equals to 1. So what can I do? So when this is going to 0, okay, when this is going to 0, when this equation is going to 0, so if I rewrite this equation, my s minus 1 equals to 0. I can rewrite like this one, right? S minus 1 equals to 0. Now I can see my s minus 1 is 0. Okay, s minus 1 is 0. So if I name some variable z, right, if I name some variable or even name it x also. We generally name it z. I can name it z, x, y, z, anything you want. So if I name some variable x which is equals to s minus 1, so now if I put s equals to 1 over here, okay, it will always be around the 0 axis line, okay, around the 0 axis line, right? So what I will do, I will change the axis, I will map this function. Basically this is used in Nyquist basically, okay. This is one of the important concepts of Nyquist. So if you understand it here, well and good, we will understand there also. So this is the concept of mapping, right? So I'm mapping my function so that I will find the roots for this one around the x j omega axis, around the left and right, and that answer will give me this answer. Let's see. So I will map x equal to s minus 1. So if x equals to s minus 1, then what is s equals to? So this is right. If I put s equals to 1, I will get 0 over here, okay. So this is the around the j omega axis. So what is my s is equals to s related in terms of x, s equals to s plus 1, right? S equals to x plus 1. So I know s equals to x plus 1. So now, right, what I will do, I will replace this s in the characteristic equation and I will use my Routh Hurwitz criterion, and then I will find the like the number of right hand roots around this x, right? And whatever right hand roots I find around this x, that will basically be my roots on the right hand side of s equals to 1, okay. So I hope you understand. Let me solve this, then also I will explain once again. So yeah, let me solve this one basically. So I have a new axis, okay, new axis I have. This is z, this is not z, sorry, z equals to basically s plus 1. So here I will find my roots around this one, right? So what does this line represent? This line represents two things. First is it represents z equals to 0, okay. Z equals to 0 it represents. Other what it represents? It represents s equals to 1 also. S equals to 1 also it represents, right? Sorry, this is did I do something wrong? S minus, no, this is s minus, sorry, this is s minus z equals to s minus 1, sorry, not s plus 1, this is s minus 1, yeah. So this represents two lines, right? Two lines, z equals to 0 and s equals to 1, okay. So from here, if I find the roots on the left hand side, so I can find the roots on the left of z equals 0 line, or I can find the roots on the left of s equals to 1. This is what I am interested at, but this I had to do to use the Routh stability criterion, right? But what is the different thing I will do? I will simply replace this z x s value in there, okay. Not right, I put x over there, so I will write x here. So yeah, this is what I will do. So simply, right, simply this will be s cube. So I will write x minus okay, sorry, this I will write as s equals to x plus 1. I will write x plus 1 whole cube, okay. Then I will write, okay, let me copy this equation itself. Okay, right, plus k. So like I will also write one more thing, that you can't simply do internal product greater than external product, this one, right? 10 times 180 greater than this k times 1, right? You can't do that. I should write this one because this will be wrong, right? Simply because we are not finding around s equals to 0. My line has changed. So this is what this is telling. This is telling us k should be less than 180, which is wrong, okay. Wrong, okay. I have s equals to 1 line, so just be mindful of that. So not s equals to 0, okay. So yeah, let me complete this equation. So this becomes x cube plus 3x square plus 3x. I hope you know like cube root. So this is 10x square plus 20x plus 10, and this is plus 18x plus 18 plus k equals 0, right? So this is what basically my equation is. Now let me further simplify this one. So if I further simplify this one, what do I get? I get x cube plus 3x square is there. Okay, I have 13x square. Okay, then what do I have? I have 3x plus 20x plus 18x. So I have this is 13x plus sorry, not 13, sorry, this is 3x plus 23x, and this is 21 and okay, 20 and 21, so 41x, right? This is 41x, so 41x. And what is the last term? So the last term is simply this one, right? I have this constant 1 plus 10 11 plus 18, right? So this is 11 29 and this is 39 basically. Okay, sorry, this is 29 itself, sorry. So this is okay, this is 10 plus 18 is 28 and plus 1. Okay, so there are too many things going on, that's why I'm just getting a bit confused. 29 should be equal to 0. Now simply you are forgetting the k also, right? You have a k also here, right? 29 plus k equals to 0. So now what you do is basically you do the internal product and external product. So basically this is the internal product and this is the external product. So for my system to be stable, for stability, my internal product should be greater than external product, right? So basically 13 times 41 should be greater than 29 plus k into 1. Okay, so it should be greater than 29 plus k into 1. So this is basically what basically internal product and external product is. So now, right, if you compute this one, what do you get? So what is 41 times 10? It is 410. Then I multiply again 3, so it is 123, right? So 410 plus 123, what do you get? 410 plus 123 is 533. Okay, then I will subtract 29, which should be greater than my k, right? So if I subtract it with 30, I get 503. I will subtract it with 29, so I will get 504. Okay, that's how you use it, right? You don't even need the calculator always. Okay, you can do mental calculation also, so that also makes your brain sharp also. So this is the condition. So my k should be basically less than 504. Is there any other condition? Yeah, other condition is there. This term should be greater, right? These are positive, so all the coefficients should be positive. Also this 29 plus k should be greater than 0. So this is greater than 0, so k has to be less than okay, am I doing this? Yeah, minus, am I doing this correct? K has to be less than minus 29, right? So k has to be okay, am I doing this correct? Sorry, I'm doing this, that's what I was confused. K has to be greater than 29, right? K has to be greater than minus 29. So basically what are the conditions? K has to be less than 504 but has to be greater than minus 29. So what is the limit of my k? K has to be greater than minus 29 but has to be less than 504. Okay, yeah. So this is what my value of k is. Okay, so yeah, I think that's it. I think, yeah, that's it for this question. So I will explain you what happened, right? So what did I do in this question? Very important question this is. So what is the question asking? I have to find the value of k. Okay, or I should write as condition of k. Okay, because the exact value I won't get. Condition such that the roots of the characteristic equation lie on the left above the s equals to 1 one line, not the s equals to 0 line. Okay, until now what we used to do, we used to find the roots on the s equals to 0 line, right, on the left hand side of the s plane. Why? Because that is what determines my stability. Okay, that is what determines my stability. Now you might ask, why am I interested in s equals to 1 line? Okay, s equals to 1 line is not like very interesting, but s equals to minus 1 line is very interesting. That we'll see when we will go into the frequency response, and we will find the relative stability parameters, right? There we'll understand why this s equals to minus 1 is very interesting. Okay, that is for another discussion. But I have to find the roots on the left hand side of the s equals to 1 line. So for that condition, what condition should my k follow so that my roots are on the left hand side of the s equals to 1 line? So I don't know how to find. I can't just simply use that internal and external product concept. So what I do, I use the concept of mapping. So I know how to find my roots on the left hand side of s equals to 0 or any variable less than 0, because this Routh criteria, right, it is applicable for any type of polynomial. Okay, it's not like it is just applicable for characteristic equation, it is applicable for any type of polynomial with coefficients, as I told in the first lecture also. Okay, so it's not like it is only applicable for this s variable. Okay, it's not like that. So what I will do, I will convert my axis something to equals to 0, and I will find that root on the left hand side. Okay, then that will be by my condition for k, right? That will be my condition for k. So this line, right, I converted my axis, mapped my axis to x equal to 0. Now for x equal to 0, I can find my Routh stability criterion, right? I am only finding for left hand side roots. Okay, so I can find my criteria, I can find my condition for x equal to 0, but this x equal to 0 also means some other line s equals to 1. So this line represents two things. One is x equals to 0 and s equals to minus 1, but I can't find my Routh condition for s equals to 1. So what I will do, I will find my Routh condition for x equal to 0. So what I have to do, I have to replace this equation, not like I have to make this equation in terms of x instead of s, right? That's how I will find my roots on the left hand side of x equals to 0, not s equals to 0. So I have to replace this one with x, but what I know internally is that my x equals to 0 is basically s equals to 1. That I know internally, right? That's what I changed here, right? Okay, I know my s minus 1 will always be equals to 0. If I equate this, if I make this equals to x, so my x is equals to 0 and x is also equals to s minus 1. Why s minus 1 is always equals to 0? You put, right, you put like s is equals to 1, right? So 1 minus 1 is 0. Okay, so yeah, exactly that is what I did. I simply mapped my function. So I found this equation, and then simply I applied the Routh criterion, right? So for this one, this will be stable, and I can apply my internal product, external product. And what does this tell us? This tells us that, okay, I will copy this one, I will cut this one. Okay, I will take another page, I will write here, this tells us the condition for roots to lie on the left half plane of s. No, right? No, this tells us the condition for my roots to lie left half plane of x, right? X. Now what is x? X is basically what? S minus 1. So also this tells us about the left of, hence, and left of this s minus 1. Okay, so if I equate this one, what is the meaning of left of s minus 1? It is s equals to 1. So I can write left of s equals to 1, right? Left of s equals to 1. Okay, so this is what basically my roots are. So I hope you got the understood the concept, right? Previous questions were very simple and easy. Just the oscillation part was a bit new. Whenever you know the oscillation frequency, you just put it in the equation, and you know, right, they will be marginally stable and they will be complex. They will be conjugate, imaginary component, imaginary conjugate. Okay. Yeah, sorry, I had to interrupt the video again, because again someone called me. So people are calling me so much these days. So yeah, now what we will do is we'll learn a new concept basically, right? And then we'll end this lecture. So first, what is that new topic? Basically the new topic is symmetry condition between the left half plane and the right half plane poles, right? So what do we mean by symmetry condition, right? There is some condition that we will follow to understand how many of my left half and right half planes will be symmetrical to each other, right? About the origin basically. So yeah, we will understand this by solving few examples. So this is the 11th question basically. So you can do this, right? Pause the video and try to find the location of the poles for this following characteristics equation, right? So yeah, now I will start. So what I will do is first write the RH table, right? So RH table, right? But before writing the RH table, what I notice is this is not in my standard format, right? It's not in my standard format because the S square coefficient is missing over here, and anyways the coefficients of these are not anyways same sign, so that we know there will be right hand side poles, but how many of them, that we have to know, right? So yeah, so first let me write this in standard format. S to the power 4 we have, right? S to the power 4 plus S cube plus 0 S square and minus S and minus 1 equals to 0. Okay, equals to 0. So this is my standard format. Now what I'll do is write my Routh table, basically compute my Routh table. So obviously I will write S to the power 4 S cube S square S to the power 1 S to the power 0, right? And this will go until here. And what are the coefficients? 1, 0 and minus 1. So I am doing fast now. Okay, so I hope you are pro at this now, become pro, right? So 1 then minus 1 or is it, yeah, sorry, yeah, it is 1, yeah, minus 1 and then 0, right? Minus 1 and 0. I have nothing over there, so it is 0. So what will come what will be the first column? Basically 1 times 0 minus 1 times 1, which is plus 1 divided by 1, so which is 1 only, right? 1. Now what is this value? Simply this one will come over here because I have a 0 over here, right? So yeah, this one will come over here and this is minus 1. And what is then what will be this one? So this I can see from right here is that it will be a 0, right? It will be 0. Okay, and this one is also 0, basically this one is also 0 because here I have 0 and this 0 is coming over here, so this one is also 0. So what do I get here? This one is row of 0, this one is row of 0, right? So if this one is row of 0, again we have to using the auxiliary equation. So basically I will write my auxiliary equation. So auxiliary equation will be this one, right? This one will be my auxiliary equation. So what is my auxiliary equation? Equals to auxiliary equation equals to S square minus 1. Okay, so this is my auxiliary equation. Now what do I do? Generally I do is the differentiation of the auxiliary equation to find the coefficients of my ROZ, right? Row of 0, to change those row of 0, right? So now we'll differentiate this auxiliary equation, okay, to find the coefficient of my ROZ, 2s and plus 0. Okay, so what do I get is this one will be 2s only, so I will copy this one. Okay, then we'll write here is this is 2 and this is 2 and this is this is only 0 only because 0 will come over here, right? 0. Okay, so that we got, right? That we got. Now let's compute the last row. So this is 2 times minus 1, 0 divided 2, so this one will come over here anyway, so that this is basically this one will come over here, which is equals to minus 1, right? Minus 1. So what do we see? How many sign changes do we see? So this is plus 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 and minus, so last row becomes minus. So I have one sign change, right? Number of sign changes equals to 1. Number of sign changes equals to 1. Okay, so yeah, I have one number of sign changes. So that we know. So number of right hand poles, how many number of right hand poles I will have? Number of right hand poles equals to 1. Number of right hand poles equals to 1 itself, right? Number of right hand poles equals to 1 itself. So yeah, that is that. Okay, now let's understand the new concept. What is the new concept? My auxiliary equation was this one, right? My auxiliary equation was this one. A of s, auxiliary equation. Right, this row was my auxiliary equation. Now the number of sign changes below the row of my auxiliary equation, okay, will give me the number of symmetric left half poles and right half poles. Let's understand that. So number of sign changes below the row of my auxiliary equation will give me the number of symmetric left half poles and right half poles. Give me the number of symmetric left half pole and right half pole pair, basically pair, right? How many pairs of them are symmetrical? Okay, around the origin, obviously around the origin. Okay, so around origin. So what is that number of signs? So this, right, this we define as m. Okay, like you can name it anything, n, m, p, whatever you write, right? So this, just to write in shortcut, we define it as m. Okay, so from now on I will write it as m. Okay, or I will just copy paste this one. Okay, so here, right, what I notice here is auxiliary equation is this row, right? And below this row, how many sign changes do I see? Sorry, auxiliary equation is this row, and below this row, how many sign changes do we see? We see one sign change. So in this, in current question, so current question, my m equals to 1. Okay, my m is equals to 1. So in my current question, my m is equals to 1. So how many symmetrical right half and like poles I will get? So I will get like I'll just copy this one, symmetric right half pole pair. Let's color this one. I will get this one as 1, right? Okay, so let's cross verify that, right? Let's cross verify that just by writing the roots of this equation. So how do I find the roots? Basically equate the auxiliary equation equals to 0, right? So auxiliary equation a of s equals to s square minus 1 equals to 0. Okay, equals to 0. So now my s is plus minus 1, right? S is plus minus 1. So if my s is plus minus 1, so I get two roots which are symmetrical about the origin, lying in the right half plane and the left half plane. So from here only I got. But now let's check for the other roots, right? Other roots. So again, right, we'll use our long division method. So to find the other roots, right? So what is my equation? Basically characteristics equation is this one, right? So I'll copy this one. I'll just not take, I will just copy this one. This one is my dividend and this one is my divisor basically. So this auxiliary equation I will divide, right, to find the other roots. This factor is already here, okay, but I need the other factors also. So yeah, this one, is this one. And yeah, let's do the long division basically. So first I will multiply by s square to get this one out of the picture, the highest coefficient. So this will be s to the power 4. This will be I don't have s square anyway, so I will just write it over here only, s square, okay. And this one will be minus and this one will be plus basically. So what do I get? I get this one as 0, I get s cube, then plus s square, then minus s minus 1, okay. Then I multiply by basically s, right, multiply by s. So if I multiply by s, I will again take this one out of my equation, right, and this is minus s. So this will be minus and this will be plus, and this is s square, and again this is minus 1, right. So again I simply multiply by 1, right. If I multiply by 1, I will get my equation. So this is s square minus 1, which is getting cancelled, right. Okay, I need to keep this one a bit above, okay. So this, my remainder will come out to be 0, and this is my quotient basically, right, quotient, and this is my factor. So this is a very famous factor basically. I hope you know the roots of this one, else you can simply use the Sridhar Acharya formula, and from there you will find that s square plus s plus 1. So s, like the roots, right, roots would I get is s will be equals to minus 0.5. Just use the Sridhar Acharya formula and you get root 3 by 2, basically minus half plus minus root 3 by 2, 0.866, okay. These are my roots. So now let's plot it in the sigma j omega plane, right. So basically s plane, sigma j omega, okay. So where does my other two roots, right, those symmetrical ones, one was here, right, in minus 1, one was here in plus 1, okay. I need to put this more closer, put this further away, okay. So yeah, and now right now, where are my other poles? Other poles lie around here, right, minus half. The real part is at minus half, plus minus, okay. I write plus minus also, plus minus under root 3 by 2, okay. So yeah, other roots lie around here. So what do I see? I see that I have two symmetrical roots, okay. This is plus 1, I see from here, right. If I can, okay, these are my two symmetrical roots basically, okay. So these are my two symmetrical roots, okay. So I hope you got the point basically, right. So yeah, from m, value of m, we can understand how many symmetrical roots are like the left half pole and the right half pole are there, right. Else they will lie on the imaginary axis itself. They will symmetrical about the imaginary axis, right. Else they will not lie around the left half and the right half, right. That's how we understand, okay. So yeah, this one is one question. Let's now pause the video and again compute the Routh table and solve the same, right. Okay, so and find the number of symmetrical poles basically, value of m, okay. So I will compute the Routh table. So here we have a complete like polynomial, okay. All the orders are given. So directly I will compute the Routh table. I'll just copy this one because it will again take me time. So each table, right. I need to bring the characteristics equation also. Here I have s cube, so s cube will be the highest power, so this will go up, and I will copy this one. Okay, I'm just copying pasting and paste this one here. So what I will do is write the basic equations. So first I have 1, then minus 1, right? Then I have 1 here, then again minus 1. Okay, so now let's compute the next row. So if you compute the next row, what do you see? You see we get a 0, right? Because this is 1 minus 1 times minus 1, which is minus 1, and this is plus 1, which is 0. So this I will get as 0. Okay, and obviously here I have nothing, right? So this will also come out to be 0, right? So again, right, we have a row of 0. Again, this one will be my auxiliary equation. Okay, but this time to check how many sign changes are there below this auxiliary equation. So what will be my auxiliary equation equals to? Auxiliary equation is equals to s square minus 1 equals to 0 again. Is it? Yeah, s square minus 1 equals to 0 again. So this is my auxiliary equation. So okay, did I write the same equation again? No. So like what is my like the coefficient of the row of 0? Coefficient of row of 0 will be a dash of s basically, which is equals to 2s, right? Coefficient is 2s. So I get coefficient as 2s. Now let me restart my computation of Routh table, right? So again I will copy this one, leave this one, and paste this one here. And what will be this? This will be basically 2, and this will be 0, right? 2 0. Okay, why? Because like the coefficient of this s is 2 itself, right? That's why. Now I compute this row. What is this one? 2 times minus 1, like this one will come over here only, right? This one will come over here only. Again I get minus 1. So this time, right, this time how many number of sign changes I have below the auxiliary equation? So here my m equals to 1, right? Okay, so I'll have one pair of like symmetrical poles of right half and the left half pole, right? So this is basically what my m is. So now, right, now let's compute the other poles, basically compute the poles basically. So what is my auxiliary equation? Auxiliary equation as equals to again s square minus 1 equals to 0, right? So if it s square minus 1 equals to 0, again I get my s equals to plus minus 1. So that is my symmetric pole basically. What are the other poles? Okay, so let's compute that. Like basically I will have only one pole right this time, right? Because this is a third order system. So like the right half poles I know. Okay, right half poles I know because how many sign changes are there? Number of sign changes plus plus minus, right? So number of sign changes 1. Hence one sign change, right? One sign change. Hence number of right half pole equals to 1 itself. Number of right half pole equals to 1 itself, right? So yeah, that is this one. Okay, so now do one thing, that let's like we know one pole is on the right hand side and this is this pole, right? This pole. So other remaining poles will be on the left hand side basically, because we have only 1 plus 1 equals to is the left, minus 1 equals to one of the symmetric poles, and I have remaining one pole. So either it can lie in the origin or it can lie in the real axis of the negative half plane, right? It cannot lie in the imaginary axis, j omega axis, or on the complex conjugate plane on the left hand side, because if some pole lies around here, there must be another pole here, right? Conjugate pair, but we have only one pole available. So either it can lie in the real axis, negative real axis, or in the origin. But origin it can't lie because all the coefficients here, right, like this coefficient, like the zero other coefficient of s, right, it is non-zero. It is not equal to 0. If it was 0, we would have a pole at origin, but this is non-zero. Hence from here we can deduce that obviously we don't have a pole at origin, we will have a pole at the negative axis only, right? Negative real axis. Okay, so but still let's compute it. So let's do the long division method again. Okay, so this time we'll do the long division method bit quickly. S square minus 1, this is s cube plus s square minus s cube minus s plus minus 1. Okay, now right, now what you do, now simply you multiply by s again. So you multiply by s, you get s cube minus s, and this will be cancelled, so this will be s square minus 1. And now again you multiply by 1, so you get, so I get repeated poles this time, right? Repeated poles. So this is basically s square minus 1 again, so this remainder will be 0. So I get s plus 1 equals to 0, right? S plus 1 is a factor, so which is equals to 0, so s equals to minus 1. So what roots I have? So my roots are basically s equals to plus 1, minus 1 and minus 1. Luckily I get a repeated root here, right? A repeated root, not a symmetrical repeated root, but a repeated root. Okay, so yeah, it may so happen. So now let's draw this in the sigma j omega plane, right? Sigma j omega plane. So from intuition, basically I told you that where will my poles lie, but like let's plot it directly by solving it. So one was at plus 1, another one is at minus 1, and another one, like this is the symmetrical one, and another one is like individual one is at minus 1 itself. So I have a repeated pole over here, right? Repeated pole over here. Okay, so yeah, this is my repeated pole. Now right now let's solve another question. So here let's see what is the value of m. Okay, the last question this is, then we will go to another types of question, right? So again, right, doing the same thing, computing the Routh table. So I will copy this equation, which is s cube minus s square plus s plus 1 equals to 0. Okay, and now what we do is we have to basically do this s cube s square s to the power 1 and s to the power 0 basically. And now what we do, 1 1 minus 1 1. Okay, so this is what we do. Now obviously compute the Routh table. So again what we see is this is sorry, did I do some mistake? Okay, this is minus 1. Okay, that's why I'm confused, like why am I not getting row of 0? So this is minus 1, so this will be also minus 1. Now simply what you get, like minus 1 times 1, then this becomes 0 itself. So again, right, you will get a row of 0 again over here, right? Again you will get a row of 0. Again this will be my auxiliary equation. Okay, again what will my auxiliary equation equals to? My auxiliary equation will be equals to, this time it's a bit different. Okay, minus s square minus 1 equals to my auxiliary equation. So the roots also will be come out to be a bit different, right? So let me check if it's recording or not. Yeah, everything is recording. Sometimes I get worried, right? So yeah, this is my auxiliary equation. Now what do you do? Simply differentiate this one. So if you differentiate this one, a dash of s equals to simply minus 2s. So a dash of s equals to minus 2s. Now let me put the coefficient in the Routh table itself. So I will copy the Routh table. Okay, I will copy the Routh table. Now this one becomes minus 2 and 0 because this is the coefficient, right? After this I have nothing. Okay, so yeah, this is this one. Now let's compute the last row basically. So again this one will come over here, right? So we'll do this with other pen. This one will come over here. Okay, minus 1 basically. So here this comes over here. Now where is my auxiliary equation? Auxiliary equation is in this, right? Auxiliary equation is in this. Okay, so how many number of sign changes I have? So let me write this. So this is plus minus minus minus. So number of sign changes, right? Number of sign change in the first column basically is 1. So number of right half poles equals to 1, right? Number of right half poles equals to 1. But how many number of sign changes do I have below my auxiliary equation? How many? I have only none, right? None. Only no, I have only none. Nothing I have. So m equals to 0. Okay. So m equals to 0 itself. So m is equals to 0. So now how many number of symmetric left half and right half poles I will have? Again none, right? So no symmetric left half pole and right half pole, right? Okay, as m is equals to 0. So now let's actually find it out and prove it for ourselves, right? So again, right, what is my auxiliary equation? Auxiliary equation is minus s minus 1 equals to 0, minus s square basically. So I have to equate this with 0 so that I can get my values of s. So it is plus minus j only. Okay, plus minus 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 under root 1 plus minus under root minus 1. Okay, and it is plus minus j only. So this basically this s square plus 1 is a factor, right? If I multiply with minus 1 on both sides, okay, both sides, it doesn't make any difference. Okay, is a factor. So again I will use the long division method to find the other root, right? Other root. So it is basically s cube, if I remember what was the equation, s cube minus s square plus s minus 1. Okay, so this is basically my what equation is, right? So now let's do the long division. Basically multiply by s, so this becomes s cube plus s. Okay, so this gets subtracted over here, so I am left with minus s square minus 1, and now if I multiply with the minus 1 I get minus s square minus 1, which becomes 0 itself. Okay, which becomes 0 itself. So if this becomes 0 itself, what do I get? Basically my s minus 1 is a factor, so s equals to 1 itself, right? S equals to 1 itself. So like I get one right up pole, which was this one. Obviously, like I got two poles on the imaginary axis. Obviously I have to get the right up pole, like one right up pole, right? Because I had number of sign changes as 1, right? So yeah, how will my sigma plus j omega plane look like? So s will be equals to 1 plus minus j, right? Plus minus j. So let me copy this one because this will again take time. Oh no. So like 1 is lying on the right hand side of 1. Okay, s equals to 1, right? And another one is lying on the plus minus j. This is minus j and this is plus j, right? Plus minus j. So like obviously from here, like from the roots I can understand I don't have any number of left hand poles. Why? Because first of it may so happen that I have left hand poles, but they will not be symmetrical because m is 0. Okay, hence no symmetricity. M is 0. M is 0. Like no left half right half pole symmetricity, but we have still symmetricity, right? Because obviously I told you when you have ROZ we will get those symmetric roots, right? But we have symmetric roots, but those are not left half pole and right half pole symmetric, or left half plane and right half plane symmetric, whatever you want to call it, right? Left half plane and right half plane symmetric. Basically no left half plane and right half plane symmetry. Okay, so yeah, from here we got our like basic proof, right, of how this happens. So now the questions have been changed. So this time, right, I am giving you the Routh table up front, right? You have to approximate the location of the roots. Obviously you can't exactly find the location of the roots. Just like, can you tell from this Routh table and information about the ROZ that where in which plane does my root location of the roots lie? Are they lying on the left half plane? Are they lying on the right half plane? Or they are on the imaginary axis? Or they are on the real axis, right? Real axis. Okay. Are they complex conjugate? Are they on the real axis? What they are? Just that, not exact locations. So this is the first question. Just take the screenshot or pause this video and solve this. Okay, and I will show you the next question also. This is the next question. Either take the screenshot and try to solve it by yourself. And this is also another question. Take the screenshot and try to solve it by yourself, right? So what I will do, I'm thinking is that I will take another lecture basically, and this I will solve. Okay, these things also, or like these are, I think these are very short only, so I can extend this lecture because yeah, you might think again training, but still I will try to let's extend this lecture only because this, I don't think this will take much time. Okay, but just a bit of explanation is needed. So this question was the first one, right? This question was the first one. So here I can see I have total two sign changes. So from the sign changes I can understand that I will have two right half plane poles. That I can understand. Right? So I will copy this one, copy this thing, right? What I can see is number of sign changes equals to 2 itself. So number of sign changes equals to 2. So if my number of sign changes is 2, then number of right half plane pole will be also 2, right? That we know. Now, is there any this is my auxiliary equation, right? So this will be my auxiliary equation. Oh, yeah, sorry, actually my tab crashed again. So this will be my auxiliary equation as I was telling, right? So this is my auxiliary equation basically, right? This is my auxiliary equation. What do I see? That number of sign changes below auxiliary equation is 1. So m is equals to 1. M is equals to 1. So symmetric. Okay, I will copy this one first. Number of, there is one left half plane and right half plane symmetricity. Okay, we'll see. We'll try to plot it and then we'll understand. So one thing is for sure, like I have two right half plane poles, and how many number of maximum poles I can have, number of roots is like this one, right? 5. So total number of roots or total number of poles, is 5. Now out of those 5, my 2 are on the right hand side. Okay, and I know that 1 will be symmetrical. So 2 are on the right hand side. So definitely 1 can be 1 is at least on the left hand side. Okay, 1 is at the left hand side. Now I have got 3. Now the 2 can be also on the imaginary, also on the left half plane, okay, but if my 2 are on the left half plane, then what will happen? So let's see. So numbers are like, I will draw the sigma plus omega axis. So now if I assume that my right hand side poles are on the real axis itself, sorry for that sound. If I assume that my right hand side poles are on the real axis itself, okay, let's see, then we will assume other cases. So if they are on the real axis, so I will have at least one pole on this left hand plane, right? One which is symmetrical around this one, okay, which will be symmetrical. So we'll mark that one basically, right? Mark that one, that will be symmetrical, right? So that I know. Okay, now I got 3 poles. Now where will my other 2 poles lie? So other 2 poles can either lie around here, okay, they can lie around here also, or they can lie around here also. But what is the problem? The problem is from the auxiliary equation, right? What is the order of the auxiliary equation? The order of the auxiliary equation So what is this? This is basically s to the power 4. So I should write this one also, take this one also here, else you'll get confused. Oh, not cut. So color this one different, or I'll color this one different. So what is the order of my auxiliary equation? So if I see, right, okay, if I just take it above, it is 4, right? It is 4. So order of auxiliary equation is A of s is 4. So what does this mean? This means that 4 roots will be symmetrical. Okay, I will have 4 symmetrical roots. Okay, 4 symmetrical roots around the origin. Now if I keep my roots here, right, then it isn't symmetrical anymore, because I got one symmetrical root but other symmetrical pair isn't symmetrical with origin. If I keep something here, so something has to be here, right? Okay, and if I keep something here, then something has to be here. So in this case, right, for this particular case, my roots can lie where? In the imaginary axis itself, right? If they lie on the imaginary axis itself, they will be symmetrical. So okay, so these are symmetrical, right? These are symmetrical, and these are basically what do you call it? Right half plane and left half plane symmetrical. Okay, so yeah, so is there any other way to draw this one? Is there any other way? So what we can do is that we can draw it like this one also. So let me again, okay, I have to again do this. I'm just simply showing you. Okay, again this is going somewhere. My tab is acting like crazy these days. It is getting worked so much. So okay, where was I? Yeah, right. Yeah. So right, so now if my two right half plane poles are like this one, so what does my left half plane poles has to lie? They have to lie like this one, right? Just to satisfy the condition of symmetricity. But what we know like here, what I understand is that two left half pole and right half plane symmetricity is happening. Okay, what does this mean? This means that my m will be equals to 2, which is not true. Okay, but my m is equals to 1, hence we will not consider this case. Obviously the other root, right, remaining root will lie around here. Okay, remaining other root will lie around here, but we will not consider this case because my m is equals to 1. Okay, will not consider this case. Okay, so this is not possible. Okay, so I hope that cleared you out a bit why I'm doing it like this one and not like that one. Okay, so yeah, let's solve the next question. So in this question, right, what do we have in this question? Basically, again, we have been given the sign changes, so I'll again copy this one because last time I didn't copy and it didn't bode well. So yeah, so yeah, now right, this is ROZ. Okay, this is ROZ. So what will be auxiliary equation? Auxiliary equation will be this one. Again, order of auxiliary equation is 4 only, right? Order of auxiliary equation is 4 only. And how many number of sign changes we have? So number of sign changes equals to 2, right? Because here I'm going here and here one sign change and one sign change. So number of sign changes is 2. Okay, I have 2 number of sign changes. And what is the order of auxiliary equation? Order of A of s equals to 4 again. 4 again, right? So I will have 4 symmetric roots. This means I will have 4 symmetric roots. Right. If I have 4 symmetric roots, now how many number of left half plane and right half plane symmetric roots I will have? So if I see, right, below my auxiliary equation, my sign changes 2. So my m equals to 2. My m is equals to 2. So number of 2 left half plane and right half plane symmetry. Okay. So basically all these 4 symmetric roots are this one only. So no roots will lie on the imaginary axis. Okay. Obviously I will have 5 roots. Okay. As there are 2 sign changes, so 2 roots are on the right hand plane and 2 roots are on the left half plane from this one. I have one remaining root that will obviously lie on the real axis of the left hand side. This can't lie on the complex axis because we have to consider a conjugate for it also, which is not possible, and can't lie on the imaginary, same reason. And origin we're ignoring the origin part. Okay. So yeah, origin we are not taking into account. So if they have told that information, if they have told, then we have to consider origin, but if nothing is said, we will not consider origin. Okay. So yeah, so how will my roots lie? So I will have basically all these 4 symmetric roots, right? All these symmetric roots, basically if I assume that 2 roots are around here, right, 2 right hand roots are around here, then due to symmetricity my 2 right hand roots will be here and the remaining right hand root will be here. Okay. The case 1, right? So this is g omega and this is sigma. Okay. So this is the case 1. Now is there any case 2? So what is the case 2? Case 2, right? If I assume they to be complex conjugate, my right half poles to be complex conjugate, that is also possible. That is totally possible because this time, right, I have the bandwidth to assume more poles, right? Okay, because I have four symmetric poles on the left half and the right half plane, so I have more bandwidth this time. So if I assume these to be my complex conjugate poles, due to symmetricity condition, here they will lie, right? So these are symmetric and these are symmetric. So I got 2 symmetric left half and right half plane poles, right? So where will the remaining pole lie? It can either lie on the origin or it can lie on the left half plane basically. So I will consider origin. So in the question itself I will write that don't consider origin. Okay, don't consider origin as a solution. Then this will make the question more precise. Okay. So yeah, I hope that cleared you out. So both of them are valid. Okay, both of them are valid itself, right? This is also valid and this is also valid. So both of them are basically valid. So this is sigma g omega. So that's why I told, right, basic approximate location of poles we can get from this. Obviously not the exact one we can't get, right? We need equations for that. I mean, we need the basically characteristics equation for that. Now again, this is the same question, I mean the similar question only. So again I will copy this one, but this time it has 7 roots, right? It has 7 roots. Okay, this time it has 7 roots. Now again, where is my auxiliary equation lying? Auxiliary equation is again, order of auxiliary equation is lying again 4, right? Auxiliary equation. So first I will write number of sign changes. So I will copy this one. Basically I'm doing the repeat case, so I will do it fast. So get this, all this I will copy. Okay, and I'll just change the data of this one. So like how many number of sign changes we have? Again, right, I see 1 sign change, 2, then 3, 4. So number of sign changes is 4. So I will have 4 right half plane poles, right? So this is 4. Okay, So number of right half plane poles equals to 4 itself. Okay, so this is this one. Now right now, what is the order of my auxiliary equation? It is 4 again, so I will have 4 symmetrical poles. That is correct. And what is m equals to 2 itself. So I will have like 4 symmetrical poles, and those 4 symmetrical poles will be like this one, only. Okay, so now let's see like how will I plot my sigma plus j omega plane, right? So yeah, so one thing you have to remember is that total roots I have 7, right? Total roots I have 7, and out of that out of that sigma j omega. So one possibility is there is that I have 4 symmetrical roots, right? 4 symmetrical roots, and out of that 4 are on the right half plane. So this is one possibility. Okay, so here let's say I have 4 and none of them are repeated because my ROZ isn't repeated. Okay, so I will have 4 right half plane roots here, right? 4 right half plane roots. Now I, according to these two, so 2 will be symmetrical, so I will choose these two to be symmetrical basically. Okay, anything you can choose symmetrical, and I have another remaining pole, so that obviously we're assuming that origin is not a solution again, right? Assume that origin is not a solution. I will bring this one a bit down. Assume origin is not a solution. Okay, so if I assume origin is not a solution, then what will be the case? Then the case will be like it will lie around here. Okay, the final root will lie around here, right? So yeah, this is one of the case. Is there any other case? There can be other case also. These 4 roots, right? They can lie like different also, because this time, right, I have 4 symmetrical roots, so they can be in complex conjugate form also. Okay, so this is the case 1. And let's do the case 2 basically. Let's do the case 2. So the case 2 is basically, again I will copy this one, right? Place this over here, right? So what if my 4 poles on the right half plane are complex conjugate itself, or they can be on the real axis also. Okay, so let's do this one first. Okay, so what I will assume is that these two, right, these two are symmetrical. Okay, so if these two are symmetrical, then what will happen? They will lie around here only, right? They will lie around here only. So the remaining pole obviously will lie around here. Okay, it is not at the origin, so remaining pole will lie on the real axis here. Okay, so yeah, this is also another case. Okay, is there any other case? So there is also another case. We still have another question left. Okay, we have two hours. I forgot that. Okay, I forgot that we still have another question left. So this lecture will go long basically. So yeah, this is case 3. So this is case 3, right? If this is case 3, so what I can do now is that I will assume that yeah, 2 are complex conjugate, and due to those 2, I'm getting symmetrical poles around here, right? Now other 2, right, can lie on the real axis itself also. That is not an issue. The remaining one will lie around here. Okay, so yeah, all these 3 cases, right, are correct. Okay, all these 3 cases are a possibility. So like MSQ can come from this question, right? So it is very important to understand what are the concepts basically. So here, right, all of them are what do you say, following the rule, right? Basically I have 4 right hand side poles, and out of those, like these 4 are symmetrical, that is following the rule. Okay, and I have like total 7 roots, and one of them is on the left hand side, right? 4 of them are on the right hand side. So all of them are following the root side. These are symmetrical. Okay, these are symmetrical. So yeah, these are also symmetrical. But can they lie on the geometric axis? No, right? Because obviously this 4 poles has gone. Okay, if I take 2 poles on the geometric axis, then what happens? Then I am left with only one pole. Okay, which is here. But I need 2 symmetrical poles around here, right? So which is not possible. If they are here, if they're here also, I need 2 symmetrical poles around here. So I have 4 poles on the right hand pole, and I can't choose anything on the geometric axis, because 4 plus 2 is 6, but I still need 2 poles here, at least minimum. But I have only one pole left. That is not possible. Okay, so hence my poles won't lie on the geometric axis this time. Okay, that I can surely say. So yeah, let's go to this question. Okay, let's go to this question. So what is this question telling us? Again, the same thing, right? We have to find the basically location of the Routh table. But what is important here is we have been given 2 ROZs. Okay, 2 ROZs. So if there are 2 ROZs, then that means we have repeated poles, right? Repeated poles. So there are repeated poles. So if there are repeated poles, so right, first let me write the number of sign changes. Again, I will copy the previous case. Okay, this one I will totally copy. Okay, and total number of roots I have 7, right? That we know. Yeah, total number of roots is 7 because it's order 7. So total number of sign changes, how many we have this time, right? It is only 2. Okay, because here no sign change, and here 1 and 2. So total number of sign changes is 2 only. Okay, so total number of right half plane poles is 2 only. So what is the order of my auxiliary equation? Order of my auxiliary equation is again 4. Okay, sorry, it is 6 this time. Okay, order of my auxiliary equation is 6, and I will get my repeated poles also, because here I have got ROZ. Okay, so order of my auxiliary equation is 6 this time. Hence I will have 6 symmetrical roots, and I have 2 ROZ, right? 2 ROZ. So I will have 2 pairs of repeated roots, right? 2 pairs of repeated roots. So 2 ROZ, hence two pairs of repeated roots, right? So I will have 2 pairs of repeated roots. So yeah, that is this one. And like m, what is m equals to? M is same only, m is equals to 2. So I will have 2 left half pole and right half pole symmetry, because basically 4 roots, right? 4 roots of those on the left half pole and right half pole. So this is very like interesting and confusing. Let's see. So like one thing we know, auxiliary equation was order 6, so 6 symmetrical roots, and out of those obviously 2 pairs will be repeated. So like out of the 6, 4 are gone. Okay, they are repeated. So if they are repeated, can they lie on the complex axis basically? So let me draw this, then we will understand. So let me copy this axis again. So here, what do I see? So if I make something around here, right, they have to be repeated. So again, I make something around here. Okay, now if I make something 2 out here, so I have to make 2 out of here also. So 4 are gone. I have 3 left. But how many are on the right of plane? 2 are on the right of plane. But what do we know? We know that they are symmetrical, right? So if they are symmetrical, here I have to have like 2 poles also, and another 2 also I have to have. Okay, because what do we know? We know 6 poles are 6 are symmetrical. That we know. Overall 6 are symmetrical, and 6 are gone over here. Okay, and 1 is remaining. But this is still not symmetrical, because still I have 2 poles left over here. So they can't lie on the complex pole. Okay, they can't lie on the complex pole. They have to lie on the real pole. Okay, because why? Because if I place something around here, right, I have to place again something around here. That is the issue. But with real, right, if I place one pole around here, that is fine. I have to, for this one pole only, I have to place one pole here. Okay, only have to place one pole here. Okay, so if I place this pole here, so due to symmetricity, this pole will lie around here also. due to symmetricity, right? Due to left half LHP and RHP symmetricity. Again, they are repeated, right? So I have like two pairs of repeated poles. So here I will get two pairs of repeated poles. So this satisfies my repeated condition, this satisfies my symmetry condition. Still I have two poles left to satisfy my symmetry condition. Where can they lie? Where can they lie? Can they lie around here? No. Why? Because my number of right half poles are 2 only. So my two poles are exhausted. Right? So can they lie around here? Can they lie around here? They can lie, right? They can lie around here. But what is the issue? I have got only 4 symmetric poles. I still need 2 symmetric poles. So they can't lie around here, because if they lie around here, I need another 2 poles here, which is not possible. At max, I can give 1 pole, right? And again, nothing can lie around here, okay? So if something lies around here, something has to lie around here due to satisfy the condition of symmetricity. But none of the poles can lie around here, because 2 poles are already gone. So where can they lie? They can lie on the imaginary axis, right? So to satisfy the condition of symmetricity, they will lie on the imaginary axis. So here they will lie on the imaginary axis, okay? So I've covered the 6 poles. I'm only remained with 1 pole, right? So the remaining pole will lie somewhere around here, okay? Because only 1 pole is left. Again, right, I will again write the same thing, that assume origin is not a solution. Okay, but I have to bring this down also to give this up. Yeah, okay. So yeah, I think that's it basically for this question, okay? So these types of question, you have to think a bit, you have to give it a thought a bit, okay? Like all these things, you have to write this down clearly, then you can totally solve this question. This type of questions can come in MSQ, so very important and conceptualize to clear the concept. So what is the concept? Basically, concept is only one thing, right? What is the concept? Concept is about M. How many number of like sign changes are there below the auxiliary equation, okay? So this is the important concept. Where did I do it? Here, right? I think here I did it. Yeah, this is a very important key point, okay? So very important point, right? Where around the origin. So this you have to remember. So very important, okay? So like you just revise the questions a bit and think it through by yourself, then also you will be able to clear the doubts. This Telegram group is always there to clear the doubts, right? So yeah, I think that's it for this chapter. Basically, Routh, Hurwitz, it's done. So next we'll do the root locus, which is another interesting chapter. So I hope you are gaining interest in control systems, and I hope you are liking the teaching teaching style. So yeah, thank you for watching, and I will see you in the next lecture.